With that, let's welcome our first talk, our first speaker, Criss, actually from the same lab as I am, from New York University, on magnetic tunnel junction as a real-time entropy source. Troy, can you share your screen?
Yes. Okay. Okay. Can you see it?
Give us a second. Yes, I can see it. Cool. All right, you can start.
Okay. Thank you, Esther, for the introduction. As she mentioned, I'm from NYU. My name is Criss, and I'm discussing our magnetic tunnel junction as a real-time entropy source with FPGA-based true random bit with an FPGA's true random bit generator. Okay. So for the past couple years, me and Professor Andy Kent and some other collaborators have been working on developing a hardware true random number generator with magnetic tunnel junctions by leveraging their double potential well between the anti-parallel and parallel state and the difference between the resistance of these two states. We're able to send a finely tuned voltage across the junction to put it into a truly random state and then read out that state by sending a smaller voltage that doesn't disturb the state of the junction, but can detect the difference in the resistances of the two states. So about a year and a half ago, with a custom FPGA daughter board in custom circuit, we were able to get this result on the right, which is 1 trillion truly random bits generated at a rate of 10 megahertz. And this was a very good result and a very big improvement on previous random number generators using this hardware. And if you want to know more about the details of the circuit and the analysis of this result, you can read about it in the paper that we published in IEEE about a year ago. And while this was a very good result, it wasn't the full extent of the true random number generator that we wanted. As you can see on the figure on the left, there's a large drift in our probability over the course of the experiment. We see the probability sort of walk up and down 4 to 5% during the several hours that we're taking data. And this, in the short timescale variance of 1 to 2% at any given point in the data, cause us to fail the NIST tests, which are the standard that we will use to determine the randomness of our bits. So our goals in this work were to stabilize the bit stream and eliminate this drift, consolidate the post-processing that we were doing to improve our data and pass the NIST tests onto the hardware, and finally to be able to consistently pass the NIST test with data taken directly off of the FPGA board while generating bits as fast as possible. And so the result I'm going to talk about is published in this paper list on the bottom that we have submitted to the Journal of Applied Physics. Okay, so our solution was to implement a feedback loop and an XOR operation on the FPGA board. So to handle the long time scale drifts, we're going to adjust the waveform that we send through the junction on the FPGA during the experiment. And to improve the accuracy of our bit stream, we're going to perform the XOR live during the data collection. Previously, we were doing an XOR on our PC after all of the data had been collected, simply taking the first half of the data and XORing it with the second half of the data. And this was effective, but this takes a long time and it was very computationally expensive. And we want to consolidate this onto the FPGA. So now we are performing the XOR by storing the every 4096 bits as the data comes in, and XORing with the next 4096 bits, and then sending the result of that to the PC. So we no longer need any post-processing of our data. So to talk a little bit more about our feedback loop, I'll talk about the waveform that we send through the junction. You can see on the inset on the top left of this figure on the left, we have a large negative reset pulse, which puts the junction into a known state very consistently. Then we have a smaller verify pulse, which verifies that we are in the state that we want to be in. And then we will have our write pulse. And this is the pulse with the amplitude that we will change with our feedback. This is the pulse that puts the junction into a truly random state, or the state with whatever probability we choose. And then we have a measure pulse where we collect and read our random bits. So you can see in the figure that we can now sweep our writing voltage from low to high and get a good characterization of the junction. And we have denoted 0 as the voltage where the probability is exactly 50%. And we are measuring the difference from that voltage when we do these measurements. So on the right, you can see a little bit more detailed view of our circuit. And we have the FPGA on the right-hand side taking data from the experiment and then sending a signal back to the digital to analog converters to change their voltages and modulate the write pulse here. So two important things to think about in our feedback are how often we want to perform the feedback. The faster we perform the feedback, the precise we can make our bits. but the more we change our writing frequency, our writing amplitude, the more correlations we induce in our data, and this will cause problems with the randomness test and cause it not to be truly random. So we found that a frequency of 1 hertz to be able to effectively stabilize the bit stream, but not induce too many correlations to cause problems in the randomness tests. And then we need to think about the acceptable error in our bit stream. We don't want to overcorrect and overchange our writing pulse. So our digital to analog converters are 12 bits and have a maximum voltage of 1.8 volts. So we can change the writing pulse by a minimum of 0.44 millivolts. And then looking at our characterization, we can measure the change in probability with this change in voltage, and we find that a change in about 0.44 millivolts corresponds to a little bit over half a percentage of difference in probability. So we will take plus and minus half a percentage to be the acceptable error in our bit stream and only change it when it goes outside of those bounds. So with the 2 parameters for our feedback, we are ready to put it to the test. And we do this with 4 bit streams of 10 to the 11 bits, all collected at 10 megahertz. We first have raw data with no XOR, no feedback. Then we will use the feedback loop, and then we will use just the XOR. And then finally, we will combine them with a run with the XOR and the feedback. So we start with no XOR, no feedback, and we see a very similar result to what we had previously. Large variance on the short time scale and a walking drift of 4 to 5% on the long time scale. So in the top panel of these plots, we will track the change in the writing voltage during the course of the experiment. When there's no feedback, this is a constant, so we see a straight line here. And this is the baseline that we are looking to improve upon. So next, we add in the feedback, and we can immediately see that we've pretty much effectively eliminated the long time scale drifts that we had while we still have the short-term variance. Now our write pulse is no longer constant, and we can see it fluctuating to account for the probability trying to drift. And we notice that the writing pulse seems to increase slightly over the course of the experiment. And we think that this is because when we're hitting this junction with a relatively large voltage over a very, very small area, we're actually changing the physical nature of the junction in such a way that causes a slightly larger write pulse to be necessary to keep the same target probability. So we've solved our long time scale problem, and now we can look at the effective in XOR on our short time scale problem. And we can see that in these stable parts in this run with just the XOR and with no feedback, that our variance has been reduced. However, we still have these drifts causing problems in our data. The XOR only produces negative errors, and we can see that now instead of these sort of slow drifts, we have these downward spikes, which will cause problems when we do the randomness tests. And they seem to be increasing in amplitude and frequency as the experiment goes on. Again, sort of contributing to the idea that as we're doing this experiment over and over again, we're changing the state of the junction in such a way that we need to modulate our write pulse a little bit more. And then finally, we have a run with the XOR and feedback. And we can see that now we've eliminated our drift, and we also have a much smaller variance in our data of about half a percentage. Again, at the top, we see a similar trend in our data of a very slight increase in writing pulse and writing voltage over the course of the experiment to compensate for the drift. But now we've sort of achieved our best possible bit stream, collecting at an effective rate of 5 megabits per second after the XOR. And these bits are taken directly off of the FPGA without any need for post-processing. So to look a little bit more at these data sets and determine if we've been successful, we will do a few different analysis. And the first is to look at the power spectrum of our data. So we take our data in chunks of 1,000 bits, add the probability, and then plot the probability of those chunks with the power spectral density. And we can see in the top left, we have in our raw data, we have what looks like a thermal noise spectrum, which is what we would expect because thermal noise is what is actually generating the randomness in our data. And then we can see that in the top right, when we add in the feedback, below the feedback frequency, our power spectrum is smoothed out and whitened, while above it, we still see what we saw previously. And then in the bottom left, we can see that the XOR reduces our power spectral density and smooths it out at the high frequencies. And then in the bottom right, we have our combined XOR and feedback, and we compare it to a pseudo-random bit generator just on Python, and we can see that it matches pretty well, especially at the high frequencies. At the low frequencies, it's much closer than we were previously, but it generates the best result. We show that by combining these two techniques, we're able to really smooth out our data towards the white noise that we see in the pseudo random number generator. Another way we can look at this is by comparing to the expected binomial, and we can see that with the XOR and the feedback, we get the by far the closest probability probability function to the expected binomial distribution. With the XOR, we can see that by making only negative errors, we have this skew to the left, showing that we can't just use an XOR to improve our data, but we also need to add in this feedback loop. And we see that our runs without the XOR have far too much variance. So again, we show that we've simulated the closest thing to truly random events by adding in XOR and feedback. Finally, we look again at the NIST tests. By sampling 1,000,000 bits near the midpoint of each data set, we run them through the NIST tests, and we can see that when we don't have an XOR, we fail miserably, and actually they fail all of the same tests and perform very similarly. Then when we add in the feedback, or we add in the XOR without feedback, we perform much better. However, near the middle of the data set, we're already starting to have these downward spikes and these fluctuations in the data, which causes a few of these tests to fail. And I noticed that as we look further in time in the data sets, especially with the XOR, more and more of the tests begin to fail. However, when we have both the feedback and the XOR, we pass all of the tests very well, and this holds for the entire data set. We're able to pass all of the NIST tests with bits taken directly off of the FPGA. So we've achieved our goal of being able to generate truly random bits without any post-processing while maintaining our speed. So we've showed that these techniques can effectively debias and improve our bit stream, and that we can generate truly random bits at a rate of 5 megabits per second over long periods of time. And we're looking into alternate ways to debias, for example, without using an XOR, which loses so much information. And we're looking for ways to speed up our bit stream and new things we can do, and new probability distributions that we can generate. And that's all. Thank you.
Thank you so much, Troy. Any questions from the chat? Or if you have a question, you can raise hand and I can unmute you. If not, I want to ask a question about like these drift that you see.
Yes.
You'll have a few minutes for a question. Do you have some sort of like idea of why we see this drift? Is it physical? Is it instrumental? Like what's happening there?
We're somewhat confident that's probably not instrumental. We've tested things like the change in probability with temperature, and it shouldn't be enough to change this. And the instruments should be good enough to not cause this much drift. We think that it's that when we're hitting such a small, tiny junction with such a large voltage, so many millions of times over the course of several hours, that we're actually changing the properties of the junction in some way that causes these drifts to happen.
Cool. We have a question from the chat from Justin. Does your increasing voltage from the feedback heat your MTJs? How is MTJ performance affected by temperature in general?
It does. We are concerned with joule heating as we send this waveform through the MTJ very quickly. The external temperature shouldn't affect it very much, as we can see that if there is joule heating, or if we are warming up the MTJ, that is also possibly what is causing these drifts.
Okay. Any more questions?